Okay, everyone, welcome back to our Calculus 3 class notes. We're now moving into section 15.7. We're still talking about triple integrals in our chapter on multiple integrals, but now we're going to talk about evaluating triple integrals by using other coordinate systems which make evaluating some integrals easier. And these coordinate systems we're going to use are cylindrical and spherical coordinates. So when doing calculations in physics, engineering, or geometry, and it involves a cylinder, a cone, or a sphere, we can often simplify our work by using cylindrical or spherical coordinates, which are introduced here. Okay, so integration in cylindrical coordinates. Definition: cylindrical coordinates represent a point P in space by ordered triples, which are r, theta, and z, in which r is always positive or 0. So these are essentially the polar coordinates, r and theta, right? R and theta are the polar coordinates for the vertical projection of P on the xy plane, and z is the height of that point. So that's the actual value on the z-axis. So essentially what cylindrical coordinates do is they use the polar coordinate system instead of the rectangular xy coordinate system, but then keep the z coordinate with it. You can imagine it comes from thinking of a typical right circular cylinder centered on the z-axis. So instead of thinking of the base of these types of cylinders are circles, so it makes much more sense to use r and theta than it does x and y. And the height of the point still makes sense to use z. So the transformations here are that we let x equal r cosine theta and y equal r sine theta. So those are the same as the polar coordinate transformations. And then z is equal to z. Or if I want to know how I would get r and theta, then r squared is x squared plus y squared, and tangent of theta is y over x. So from section 15.4 then, if I want the integral of f over a domain D like I see above, then what happens is the r dr d theta becomes the dx dy, so that stays the same, and then I just have to throw a dz in there with it. So it's dz r dr d theta. So as an example, let's revisit that example that took me 3 videos to walk through, where we ended up having to do a trig substitution, but I will finish it in this many steps. So we're using the cylindrical coordinate system, and it makes it a lot easier because this lends itself to a very simple integration with the cylindrical coordinate system. So we want to find the volume of the region D enclosed by the surfaces z equals x squared plus y squared and z equals 8 minus x squared minus y squared. So recall the sketch. It's like this egg-shaped region, and then the shadow of the region onto the xy plane gives this circle, which lets us say, hey, we should probably use cylindrical coordinates as long as the surfaces can be described with cylindrical coordinates fairly easily, which they both can, super easy, because z equals 8 minus x squared minus y squared is the same as 8 minus r squared, and z equals x squared plus y squared is the same as z equals r squared. Okay, so now, instead of dz dy dx, I'm going to have dz r dr d theta, and then I'm going to be integrating for the z from r squared to 8 minus r squared. So the lower surface is r squared, the upper surface is 8 minus r squared. And then the region in the xy plane, simplified as a polar region, is then r goes from 0 to 2, and theta goes from 0 to 2 pi to sweep out that whole region. So this becomes a very simple integration. I first integrate with respect to z, and I get z. Evaluate it from r squared to 8 minus r squared. Evaluate it using the fundamental theorem. That simplifies to 8 minus 2r squared. I still have my r from the r dr d theta, so I'll distribute that through now. It's 8r minus 2r cubed. Integrate each one of these now with respect to r. Get 4r squared minus 1/2 r to the 4th. Evaluate that from r equals 0 to r equals 2. That results in 8. So integrate 8 d theta, I get 8 theta from 0 to 2 pi, and I get 16 pi. Wow, definitely much easier. And so we want to, from now on, when we see something that lends itself to using cylindrical coordinates instead of keeping it in the rectangular coordinate system, we want to take advantage of that.